So let's start with example 5 here. Direct calculations show that omega equals -1/2 plus I times the square root of 3 over 2 satisfies both of these equations. Before we get into understanding the Galois group of a certain extension relating to the omega, we should talk a little bit about what's going on here. What is this omega? You can see it as a complex number. It is a cube root of 1. Let's think about what we've talked about with the geometry of complex roots. We know that given any non-zero number, like 1, say this is the unit circle right here. So this is the real axis and the imaginary axis in the complex plane. That's the number 1, the real number 1. Any non-zero complex number, which includes non-zero real numbers, has actually 3 cube roots. Certainly 1 is the cube root of itself. That would be the real cube root of 1, right? 1 cubed is 1. But it's got 2 other cube roots that are both complex non-real numbers. And like I said the other day, they have to form an equilateral triangle centered at the origin. The other 2 would have to be right here and here. And yes, this would be an equilateral triangle. Isn't that cool? Isn't that pretty? And if that's the case, you know, of course, there's 360 degrees around the circle. 360 divided by 3 is 120 degrees. This angle right here would have to be 120 degrees, which is what? 2 pi over 3 radians. This one right here could be thought of as negative 120 degrees, but you also could think of it as 240 degrees. 240 degrees, and that would be 4 pi over 3 radians. 4 pi over 3 radians. And if you use trigonometry effectively of the unit circle, you realize that this one's got to be the number, I'll go ahead and use degrees, cosine of 120 degrees plus I sine of 120 degrees. It's essentially polar coordinates there. We are on the unit circle, so the distance to the origin would be 1. I don't need like some number in front of this expression. Cosine of 120 degrees is the first coordinate of this point, and sine of 120 degrees is the second. And if you've memorized your trig well enough by helping tutor calc students, you know that's -1/2 plus square root of 3 over 2i. And that is the omega. That's omega right there. And this number right here is -1/2 minus square root of 3 over 2i. That's actually the same as omega squared. Is that obvious? Well, remember I said the geometric interpretation of complex number multiplication is that you add the angles and you multiply the distances to the origin. These things are on the unit circle, so the distance to the origin is 1. If I square omega, I'm going to get a number whose distance to the origin is still 1. It's going to be on the unit circle. And I got to add 120 degrees to itself to get the right angle, 240 degrees. So this is omega squared. It also happens to be the complex conjugate of omega, which is often written omega bar. Complex conjugate is where you take the complex number, in this case, -1/2 plus square root of 3 over 2i, and whatever the sign is right there, you negate it. So it's a plus sign there, so you make it a minus sign here. If it had been a minus sign, you'd change it to a plus. These are complex conjugates of each other. You could also write the complex conjugate of the complex conjugate is the original number. You could write that kind of thing too. All right. Just some basic facts about complex arithmetic. So yeah, this is a cube root of 1. They say you can also check this by direct calculations. Is that worth doing? I think so, because I'd like to also check that it satisfies this equation too. So let's go ahead and compute omega squared. Well, I'm claiming it's this. Let's double check that by actually expanding it out. Omega squared would be this number times itself. If you don't have much experience with complex arithmetic, it's definitely not obvious that you're going to get that. with the minus sign there, but let's see what happens. FOIL it out. -1/2 times -1/2 is +1/4. The outside times outside and inside times inside terms are not going to cancel here. I was thinking it was the complex conjugate. They're not going to cancel here. You have to actually write them. Outside times outside is going to be -√3/4i, right? Product of these two things. And inside times inside's not going to cancel. It's going to be the exact same thing. -√3/4i. And then last times last, √3/2 squared would be 3/4. And then I squared is -1. So we get -3/4 with last times last. Right? Double check that in your mind. √3 squared is 3. 2 squared is 4. I squared is -1. So you got to get -3/4. Simplify. 1/4 minus 3/4 is -1/2. And √3/4i minus √3/5, -√3/4i minus √3/4i is -√3/2i. Right? I had trouble saying all that, but that's what it is. So we verified, yes, omega squared is this number, which is right there. And okay. Is omega squared plus omega plus 1 equal to 0? Omega squared plus omega plus 1 is -1/2 minus √3/2i plus -1/2 plus √3/2i plus 1. Cancel. And then the -1/2s cancel with the 1. Giving you 0. Cool, huh? You could also use the quadratic formula on this thing to verify what omega is, up to a plus or minus sign at least. In fact, omega squared also satisfies this equation, evidently. And omega cubed, if we want extra confirmation, omega cubed is supposed to be 1. That's the same as omega times omega squared. And so we got to do this product. Right? There's omega squared. So we'll get, again, 1/4. Yeah, now the outside and inside products do cancel. Outside times outside is plus √3/4. Inside times inside is minus √3/4. I forgot my I here. Those cancel. Last times last is going to give you plus 3/4, 1. Right? The product of those two gives you 3/4, -3/4 times I squared, but I squared is -1. So you get positive 3/4. So we are getting 1. All right, so we've just practiced a little complex arithmetic, which you should be able to do on the test. And then we want to get back to Galois theory here, evidently. So this was background, needed to consider this extension of Q. We may describe the automorphisms of that field extension by specifying how they act on omega and cube root of 2. Let's think about that again. First of all, remember exercise 1, which you should also be able to do for the test. You should make sure you study exercise 1. If you got your field extension of the rationals, any automorphism of such a field extension will automatically fix all the elements of Q. That's the content of exercise 1. Let E be an extension of Q. Show that any automorphism of E acts as the identity on Q, meaning mapping every rational number to itself. It's based on operation preserving properties. Okay, and it's in the solution key. You should practice that one. And you should also know it. Could be a new kind of true-false question, for example, or multiple choice. So that's part of the reason why this statement is accurate. describe the automorphisms of this by specifying how they act on these two things. But that's not completely the reason. What else could we say? Now, this is a little tricky here. What's the degree of this extension, first of all? And maybe we want to think about it step by step. And this is where things got tricky the other day too. So it always feels like it's like, am I doing this right? Or not? So we're after understanding the field extension Q adjoin omega Q root of 2. Again, let's think about that as first do Q adjoin omega, then adjoin Q root of 2 to that. I put an extra set of parentheses in there for emphasis. Not that you have to. So in a field lattice or tower of fields, I could start a partial lattice diagram for this extension this way. It's not the complete lattice diagram. It's a partial one. Partial lattice diagram. And I would like to fill in the degrees of these extensions. I'd like to put numbers by these lines here, telling me the degree. And I could have, by the way, I could have done it the other way around. I could have done Q of Q root of 2 here instead of Q of omega. That is another intermediate field that I haven't drawn on the diagram, and I could have thought about it that way. Let's try thinking about it this way, though. So the question is, as far as the degree of this extension, is what is the minimal polynomial of omega over Q, meaning the smallest degree polynomial with coefficients in the rational numbers that omega is a root of and it's irreducible over Q. And that is given by the fact that omega squared plus omega plus 1 is 0. Your minimal polynomial is essentially that right there. F of x equals x squared plus x plus 1 in the ring QX is irreducible over QY. You can't apply Eisenstein's criterion directly to it. You could maybe try a mod 2 or mod 3 irreducibility test. Would mod 2 work? Yeah, mod 2 actually would work. That would be enough to verify this is irreducible over Q. So it would be irreducible over Z2 because it doesn't have any roots in Z2. It also doesn't have any, you don't have to think about the mod P irreducibility test. You know, if you use the quadratic formula, the roots of this are complex non-rational numbers. They are omega and omega squared. So it can't be factored over Q. It's irreducible over Q. And we know F of omega is 0. We already know that. So F of x is since it's also what's called monic, meaning the coefficient of x squared is 1, is what's called the minimal polynomial for F of x over Q. And in fact, Q of omega is going to be the splitting field for this polynomial over Q. The other root, omega squared, is also in there because I mean, you don't see an omega squared, but since this thing is a field, if it's got omega, it's got to have omega squared because it's closed under multiplication. Does that make sense? That's the kind of thinking you got to do here. That's the kind of logic that's really important, and you want to become kind of natural to get better at this. Omega's in there, but so is omega squared because it's a field. So f of x splits in there, and it would certainly be the minimal extension when it splits. The degree of f is 2. Degree of fx is 2. Therefore, the degree of the extension q of omega over q is 2. And I can put a 2 there. What about the degree of this one? Claim the degree of this one is 3. Cube root of 2 is a 0 of, call it g of x equals x cubed minus 2, which is certainly an element of this ring right there. But more relevant for what we're talking about here with this extension, it's also could be thought of as an element of this ring. Notice the notation you see there. That's purposeful. Q of omega, Q adjoint omega, is the field I'm thinking about here as being the coefficients. Of course, the coefficients are actually rational numbers as well. The x there is in square brackets. This is a polynomial ring. And g of x is irreducible over q of omega. It's also irreducible over q. Could we use one of our tests to prove that? Not really, like the Eisenstein or mod p irreducibility test, because that's not q. But what you could say is you could factor this, and for sure cube root of 2 is not in there. You could show the other roots are not in there, because if you factor it, and this is what we did partially last time because it's a difference of 2 cubes. You could show the quadratic that's left over has no roots in there either with the quadratic formula. Yeah, we did this last time. We wrote the x cubed minus 2 as x minus the cube root of 2, and then we also wrote times x squared plus cube root of 2 times x plus cube root of 2 squared. And you could write this as 2 to the 1/3 power and 2 to the 2/3 power if you like. And if you use the quadratic formula, you have to find the other roots. They're not going to be in q of omega, though maybe that's not completely obvious. And they involve cube roots, so hopefully it's intuitive that they're not in there, because omega involves just square roots. There's omega. So hopefully it's pretty intuitive without proof that it's not going to be, the other roots are not going to be in q of omega. So this will be irreducible over that because of that. And this is degree 3, this g of x. Therefore, yeah, that extension is degree 3. Symbolically, I could also write this. You should know what the symbols mean. The notation is a big thing for the exam as well. Make sure you're comfortable with all these things I'm writing as far as what it means. So ultimately, the degree of the overall extension is 6, 3 times 2. Which would mean what? It would mean we could write everything in this field as a linear combination of 6 basis elements. What are those basis elements? It's a very long-winded explanation of this comment here, isn't it? But I think good, because it's reviewing things we've been learning. Q of omega, q root of 2. How can we represent numbers in this field? It is related actually to a certain proof from earlier. It was the theorem about the multiplicative property of field extensions, of finite field extensions. This one here. K is a finite extension field of E, and E is a finite extension field of F. Then K is a finite extension field of F, the smallest one, and the overall degree is the product of the smaller degrees. This is what we just used to say 6 is 2 times 3. And in the proof of this, what you do is you create a basis of the overall extension by taking the two individual bases and multiplying all the elements. So if this has n elements and this has m elements, you're going to get n times m products here. One element of the basis is 1. Another element is omega. Another element is cube root of 2. We would also have, well, cube root of 2 squared, which again, you can write with power notation instead if you prefer. We would also have omega times cube root of 2. And finally, omega times cube root of 2 squared. 1 omega cube root of 2 squared, omega cube root of 2, and omega cube root of 2 squared. Those 6 numbers form a basis for this as a vector space over the rationals. This is a way to represent this as A, B, C, D, and F vary over the rationals. E is not the number E, F is not a function. Okay. Those are all rational numbers. And this, again, along with the fact that automorphisms of this field are going to fix every rational number, is enough to say, to justify that comment. Because if you apply an arbitrary automorphism to such a linear combination, this is worth writing completely out here. By the fact that it's operation preserving and fixes the rational numbers, fixes A, B, C, D, E, and F, you're going to get, through a little bit of work, A plus B omega, or phi of omega, plus C phi of cube root of 2, plus D phi of cube root of 2 squared, plus E phi of omega times phi of cube root of 2, plus F phi of omega times phi of cube root of 2 squared. There's a calculation using the fact that phi is operation preserving, using the fact that it fixes the rational numbers A, B, C, D, E, and F to justify that, yeah, if we know what phi does to omega and what phi does to cube root of 2, then it completely defines the automorphism. Wow. Long-winded, but worth doing to review these things we've been learning. That means there are 6 in all. Remember also the comment from the other day that such an automorphism has to permute roots of a given equation. So omega could get mapped to itself, or it could get mapped to omega squared, but omega is not going to get mapped to cube root of 2 or cube root of 2 squared. I guess a root of these equations, as is omega squared, a root of both of these equations, by the way. Yeah, I said that. It was a root of this one. Omega squared is a root of that one too. Right, omega squared cubed is omega to the 6th, which is 1. Did you?
My computer's dead. So.
Your computer's dead. Okay. On your phone? Okay. 1 omega squared. You should also know for the test forms a cyclic group of order 3. Right? 1 omega squared is a group under multiplication. Yeah, omega squared is another root of this. Is it working?
Yeah, there we go.
Okay. So coming back here again. Yeah, it's permuting the omegas among an omega squared. It's permuting cube root of 2 to either itself or cube root of 2 squared. No, not cube root of 2 squared. Or omega times cube root of 2 or omega squared times cube root of 2. Why not cube root of 2 squared? Oh, because cube root of 2 squared does not satisfy that equation. That's one. The other roots of that equation come from using the quadratic formula on this, and those do turn out to be omega times cube root of 2 and omega squared times cube root of 2. Is that worth checking? I'll let you check that on your own if you want. You can remember it's about 30 minutes into the video or so here. Actually, I think we started at 3 minutes and 27 minutes into the video here today. If you want to double check those, omega cube root of 2 and omega squared cube root of 2 are both, I think, what you should get for the other roots of this from the quadratic formula. So because of all that, these are the 6 possibilities. Call that one epsilon because it's the identity. Call that one alpha, call that one beta. Is this one really beta squared? Think about it. If beta maps omega to omega, then it's certainly going to map, beta squared is going to map omega to omega. If beta maps cube root of 2 to omega times cube root of 2, what's going to map cube root of 2? What's beta squared going to map cube root of 2 to? Evidently that. Why? Beta squared of cube root of 2 is beta of cube root of 2. This is not a squaring multiplication. It's a function composition. Remind yourself of that. Beta of cube root of 2 is by definition omega times beta of cube root of 2 is omega times cube root of 2. Beta is operation preserving. So you can write this. It maps omega to itself. It maps cube root of 2 to omega times cube root of 2. It's not omega cubed there. It's a cube root of 2. And that's omega squared times cube root of 2. There's a quick verification that beta squared maps cube root of 2 to omega squared times cube root of 2 as is claimed here. I mean, you got to check these things. Don't just, I mean, if you want to get stuff out of this, don't just take this on faith. Claim is alpha compose beta maps omega to omega squared and cube root of 2 to omega squared cube root of 2. And alpha compose beta squared does that. Those things should be checked. So the Galois group consists of these 6 automorphisms as a group under function composition. And it sort of seems to be hinting that it's not Z6, right? By the fact that we're writing these automorphisms in these ways. And we know there are only two groups up to isomorphism of order 6, Z6 and D3. Dihedral group symmetries of an equilateral triangle. Same as S3, symmetric group on 3 objects. It's got to be D3 or S3. It's not cyclic. Here's the lattice diagram, subgroup lattice. If it had been a cyclic group, it would not be this complicated. A cyclic group like Z6 has a lattice diagram that's simpler. It's got a unique subgroup of order 2 and a unique subgroup of order 3 that are not subgroups of each other. The unique subgroup of order 2 is this, but I'm doing group theory here now. The unique subgroup of order 3 is the cyclic subgroup generated by 2. It's that. C6 is 0, 1, 2, 3, 4, and 5. And then it's got the trivial subgroup just containing a 0. That's the lattice diagram for a cyclic group of order 6. Only one subgroup of each order. That's the fundamental theorem of cyclic groups. Yeah, S3 or D3, however you want to think about it, is more complicated. You got 4 subgroups that are intermediate. This one has order 3. These 3 have order 2 because there's 2 elements of order 3 and there's 3 elements of order 2, it turns out. Alpha, beta squared are the elements of order 2. They generate cyclic subgroups of order 2. Beta and beta squared are elements of order 3. They generate a cyclic subgroup of order 3. These numbers represent the indices of these subgroups in the bigger group, right? That's the number of cosets. A subgroup of order 3 and a group of order 6 has 2 cosets. 6 divided by 3. That's why there's a 2 there. These have order 2. The number of left cosets is 3. 6 divided by 2 is 3. So you get a bunch of 3s. And then the number of cosets of the trivial subgroup in each of these is 3 divided by 1 is 3. And each of these is 2 divided by 1, 2 each time. And the fundamental theorem of Galois theory then allows us to relate this diagram to the subfield lattice diagram, or again, you could call it a tower of fields. I keep saying tower of fields because that's how my teachers called it. You get from here to here by essentially inverting the diagram. So this 3 becomes that 3. This 2 becomes that 2. These 3s become these 3s, and this 2 becomes these 2s become these 2s. And the fields that you put in these spots are the fixed fields. So Q down here is the fixed field of the entire Galois group. What are all the elements of this that are fixed by all of these things? It's only the rational numbers. That's why there's a Q at the bottom corresponding to the entire Gauss group. Remember, it's inverted. The entire field extension at the top corresponds to the epsilon at the bottom. What's the fixed field of epsilon? Epsilon maps everything in the bigger field to itself, so it's the fixed field. Evidently, Q of omega is the fixed field for that. Do beta and beta squared map they certainly map every rational to themselves. Do they map omega and omega squared to themselves? Well, look at the chart. Omega gets mapped to itself under both beta and beta squared. So would omega squared. Right. Beta squared. Beta of omega squared is going to be beta of omega times beta of omega, because it's operation preserving and it's mapping omega to itself, so that gets mapped ultimately to omega squared. Similar kind of thing would happen with beta squared. This thing is evidently the fixed field of that. What does alpha do? It does not fix mega or omega squared. It fixes cube root of 2. This thing is evidently the fixed field of that. Look at alpha beta. It doesn't fix omega individually. It also doesn't fix cube root of 2 individually, but this seems to be claiming it fixes the product omega times cube root of 2. Let's check that. Alpha beta of omega times cube root of 2. I don't even have to write this as alpha composed beta. You can just think of alpha beta as an individual element. Alpha beta is operation preserving. I could write this. And then use the chart. Alpha beta of omega is omega squared. Alpha beta of cube root of 2 is omega squared times cube root of 2. That's omega to the 4th times cube root of 2. But omega to the 4th is omega. Since omega cubed is 1. The reason for that. So yes, ultimately, alpha beta did fix omega times cube root of 2, which is a partial justification of that being the fixed field there. You probably want to verify it does not fix omega squared times cube root of 2, because evidently that's what fixes that. Now, I said we were thinking about this in the context of the fundamental theorem of Galois theory without actually looking at the theorem. I do want you to know that that's only justified when this is a splitting field for a polynomial over Q. Did we verify that? Not really. And the author doesn't seem to verify it either. This would have to be the splitting field for some 6th degree polynomial over Q. We did not write down the 6th degree polynomial. Is it possibly the product of f of x and g of x? There's g of x. Where's f of x? Did I write it down? I mean, f of x is, I thought I wrote it down somewhere. F of x is essentially, well, there it is. Okay. Would it be the splitting field for the product of those two? Yeah, it would actually. Because it's going to have all the roots of the product, because it's going to have the roots of this are cube root of 2, omega times cube root of 2, and omega squared times cube root of 2. And the roots of this are omega and omega squared. So yeah, f of x will completely split in here. And that'll be the minimal field extension in which f of x splits. So it will be a splitting field. And so therefore the fundamental theorem of Galois theory does apply. E has got to be the splitting field over f for some polynomial in there.